This week and next week, we're going to be focused on this region in Colombia. We're going to be producing ground motion fields for Colombia, a part of Colombia in a particular fault that crosses Colombia. So Colombia is a South American country. This is the location of Colombia. And we are focused on this department, which is called Antioquia. Okay, Antioquia is the department where Medellin, one of the biggest cities of Colombia, is. And we are going to be modeling a rupture very close to the city of Medellin. So we're going to model, so this is the fault. We have several faults crossing the department. For a particular fault, we're going to model a rupture in that fault. And then these are the characteristics of the event. So this is a magnitude 7 event. It has its strike, dip, and break defined. As I was saying, maybe seismologists came together and they defined this. They understand which parameters, if this is a historical earthquake, they understand more or less which parameters were observed from the rupture, which was the epicenter and the depth. And we are also going to choose the ground motion models to make the simulations of ground shaking. Particularly, we're going to use ACAR Canyon 2010, ACAR with hypocentral distance 2014, and IDRIS 2014. Always the question is, okay, so this is a real exercise. This is a real exercise. A real seismologist decided these parameters, and this is a real event. The answer is no. This is an event that will highlight the difference between the GMPs. So this is not a real case study. It's an invented case study that we chose in order to highlight what are the different consequences of me taking different modeling decisions. In this case, ACAR Canyon uses a certain distance to the fault. ACAR with hypocentral distance uses another type of distance, and then we will compare the estimates of ground shaking coming from one and another. So we understand what is the difference by using different GMPs or ground motion models. So we said that we need to prepare a seismic rupture, define the GMPs that we want to use, the side effects, if there are any, we need to define them, put all of that in OpenQuake, and this will produce for us the ground motion fields. So this is what we're going to do. How do we start defining the input parameters for OpenQuake? I am going to leave the presentation. I leave the presentation and I will show you my desktop. So this is my desktop. In my desktop, because I have installed OpenQuake, you will see that I have two logos that represent the OpenQuake engine. There is a black and white logo, which is the OpenQuake engine console, and there is a white and blue logo, which is the OpenQuake Web UI user interface. Okay, the Web UI user interface is the interface that we use for the workshops. It's a friendly user interface. Let's see. You just need to double click on it, and then the engine will start by itself. You will see a console appearing, something like this. And then the engine will open within some seconds. It will open in your browser. Okay. So let me see in which of all the windows that I have it open. Okay, it's here. So this is the OpenQuake. When I double click on the blue and white icon, a new window in my browser appears. Okay, so double click on there and see if the window appears. For those of you who installed a 3.16 version of OpenQuake, and this is the version that we should have installed for the workshop, you should know that the version 3.16 is our newest release of OpenQuake. And this has been widely tested by us at the GEM Foundation, but this is the first workshop training lesson where we are using this version. So it's the first time so many users are using it together with us. So we can expect some bugs to be there, and that is great. We love identifying these bugs during these sessions because they allow us to fix them and then improve the tool for future users. So for example, we already received some messages of people who are saying double click on the white and blue icon is not bringing me the OpenQuake web user interface, which is this one. So if that is, you're having this issue, you double click on the white and blue icon and this window is not appearing. We can still bring it up. It's very simple. You just double click on the black and white icon of OpenQuake. What is that? The black and white icon of OpenQuake is the OpenQuake console. This is how expert users use OpenQuake. There is a user interface for intermediate users, let's say, but for expert users, there is the console. Through the console, we can execute any calculation that we want. We can check the calculations that we have previously done. We can see the outputs of any calculation. The console is the way experts use OpenQuake. So through the console, we can also bring up the user interface. So to bring up the user interface, if the black and blue icon, double click on this icon is not working for you, you will click on the white and black icon 2 times. This will bring the OpenQuake console. It will look like this. And here you just need to do the following command, OQ web UE start. And then you click on enter, okay? And this is going to bring you the web UE. Again, the web UE will look like this. So if you are unable to see the web UE, you haven't been able to bring it up, remember that you can do it through the console. The command is OQ web UE start, and then you hit enter, and then this will appear. You will see this window appear where the web UE will appear through your browser. So it's not like I'm starting an external software that opens a new window. It will usually appear in your browser. So you should see it if you're using Mozilla, you will see it in Mozilla. If you're using Chrome, you will see it appear in Chrome. Is there anyone who hasn't been able to? Thank you, Kata. I can see that in the chat you already shared how to open the web UE. Sometimes the web UE doesn't run because you're not an administrator. That's a very good comment from Priyanka. Remember that you need to right click on an icon and run as administrator if you want to have administrator privileges to run. So you right click on this and then you run as administrator. Then you input the password of the administrator and then it will run the app with administrator privileges, and most likely this will solve your issue. So right now, whoever is not seeing the OpenQuake web UE, please raise your hand or let us know in the chat so we can provide, again, some assistance to you. If you need me to repeat the process to bring it up, just let us know. I don't see hands raised, so I think everyone is here. Very good news. This is it. This is the OpenQuake Engine Web UE user interface. So in the Web UE Engine user interface, if we are using an outdated version of the software, we will see a message somewhere around here telling us, by the way, there's a new version of OpenQuake if you want to update. In this case, we're not seeing it because I am using 3.16, which is the newest version of the engine. The engine itself, the web UE interface looks like this. It has a list of the calculations that are in my computer, and any calculation that I do will appear here. A common question that we get asked is, so I'm using this on the browser, right? This is my Chrome or my Mozilla web browser, and this is a window in that browser, which means that I need an internet connection to be able to use OpenQuake. The answer is no, you do not need an internet connection to use OpenQuake. If OpenQuake is installed on your computer, you can use it without being connected to the internet. The proof of that is that if you see the URL that you're connected to, it's actually the engine in your machine. So we're just using a browser to use the engine, but the engine itself does not need an internet connection. So the user interface looks like this. If you have run calculations before, there are some OpenQuake users, frequent users here. We saw that. So you will see your calculations appearing. When we start doing the calculations today, we will see that they will appear here. That's perfect. There are 2 buttons in the user interface. One is very simple, run a calculation. We are going to click here when we have all the input parameters ready to run the calculation. So the run button will allow me to run a calculation that is already prepared. it has all the input parameters prepared. This is not the case now because we said we need to define the rupture and choose GMPs. So we need to do that first. We need to come up with the input parameters for the engine. To provide the input parameters for the engine, we're going to use today the button that is called Tools. Kata, just to remind you, if we are resuming the recording, if you're resuming the recording, we can start now.
Yes, it's fine.
Thank you. So let's use the Tools button. The recommendation always is right-click on the Tools button and open it as a secondary tab. That allows me to have the OpenQuake engine in one tab and the input preparation toolkit on the other tab. Okay, so again, to bring up the input preparation toolkit, when I am in the web user interface main window, I have two buttons, Run Calculation and Tools. You right-click on Tools and you open it as a new window. Okay, so you click on Open as a new window, and that way you have the Input Preparation Toolkit, or IPT for short, in one window and the engine on the other. This will be very useful. So try to have both tabs here. Very good. Input Preparation Toolkit, or IPT for short, is a toolkit that comes bundled with the engine and will help you generate the input files that OpenQuake needs. OpenQuake is a calculator, which means I need to give it everything it needs. The rupture, the GMPs that I chose, the type of calculator that I want to use. So we need to prepare all of this information, and the IPT is the user-friendly way of doing that. Okay, so today we will be using the user-friendly way of doing it. And today we are going to start with earthquake rupture. So there are different tabs here. We have exposure, fragility, consequence, vulnerability, earthquake rupture, and configuration file. You are going to click on the one that says earthquake rupture. What does the earthquake rupture tab does? When I want to use the scenario calculator, I have to define the rupture and choose the GMPs. Through the earthquake rupture tab, I can ask OpenQuake, generate a rupture file, a file that has all the parameters of the rupture for for OpenQuake, using this tab. So it comes, you click on the tab, and you will see that here we can provide the magnitude, the rake, the hypocenter, longitude and latitude, basically the location, the depth of the event, what type of rupture we're modeling, and then we will be able to convert all those parameters that I am inputting here into a rupture file that OpenQuake can read. So let's go ahead and do that. We're going to be modeling today this event that I was showing you before. I'm going back to the event tab. Okay, so this is the event that we will be modeling today. So the first parameter that we will input in the earthquake rupture tab is the magnitude. Okay, so magnitude for us today is 7.0 earthquake. Okay, so we're going to do, just give me 1 second because the Zoom tab is in the middle of everything I need to do. Okay, so we're going to be using the input preparation toolkit. The magnitude of the event for today is 7.0. Okay, so we're going to input that magnitude there. What is the rake that we will be using today? In other words, I'm modeling two blocks that are moving, right? Does the block sleeping has a rotary component? Like, is it rotating during the slippage? And the answer is no. There is zero slippage. There is zero rake angle, let's say. So we're going to put a zero in the rake. Okay, so the first two parameters are there. If anyone is lost or I'm going too fast, please let me know. Hypocenter, we will be inputting the longitude and the latitude of the hypocenter. We basically need a location, and that can be defined by those 2 points. So hypocenter is negative 75.68 latitude, longitude, and 6.20 latitude.
Ale, I think you muted yourself. No, you are still muted.
Now, can you hear me?
Yes, now we can hear you.
Thank you. So we were saying negative 75.68, longitude negative 75.68, and latitude we have 6.20. Okay, so latitude we're going to put 6.20. Let me go back here. 6.20. Okay, what is the depth of the earthquake that we're modeling today? So the depth of the earthquake is 15 kilometers. Okay, so we go back to the top. Let me just, maybe I can put it like here and zooming a little bit. Here I have them side by side. Okay, perfect. So longitude negative 75.68, latitude 6.20, and the depth will be 15 kilometers. Okay, again, these parameters were given to us by the seismologist, the hazard modeler, the person who has already identified that this is a potential source of seismicity. This is a particular rupture that is of importance to the city of Medellin. And then in order to understand risk, prepare, mitigate, we're going to model this rupture as it is. And now with all this information, OpenQuake is almost ready to generate the rupture. OpenQuake never models earthquakes as points. This is an important distinction to do. There are some softwares out there where you just put a point along to the latitude and then it takes that point as an earthquake. OpenQuake never does that. Even if you only have longitude, latitude, hypocenter, OpenQuake will generate an actual two-dimensional fault plane and the rupture of the earthquake that is occurring. Okay, so earthquakes are always generated in OpenQuake as never as points, always as two-dimensional or three-dimensional rupture planes. Okay, so there are many ways. We have many options when we're modeling a rupture in OpenQuake. The first one is, and is the one that we will be using today, is the option for arbitrary fault rupture. Arbitrary fault rupture means that when I am modeling the event, I only have magnitudes, location of the epicenter, and the depth. Okay, and then obviously my angles, rake, deep, strike. So OpenQuake, using those parameters, will arbitrarily generate a rupture that is bounded by those parameters. Okay, so it's never a point. It will artificially generate the rupture. But we can also have more information about the rupture. Let's say the seismologist is telling me how much is the surface of the rupture, what is the trace of the rupture on the surface. If we have more information about the rupture, we don't have to ask OpenQuake to arbitrarily generate the fault rupture. We can model it point by point, that 2D surface of the rupture. There is also a way, so we have that option to generate simple or multiple planar ruptures. So sometimes a rupture is not just one plane, but it can have multiple planars, multiple planes. Let's say a complex rupture that has more than one plane of the rupture. So if there's more than one plane, I can model that. I can also model a more complex rupture. So instead of having a two-dimensional planar rupture, I can have an entire volume where the rupture is occurring. Let's say this is if we're modeling a subduction event and I have a lot of information about it from the seismologist, I can also model all of that. So the comment here is that the more information you have about the rupture, the better your estimate will be, but also you require more input from your seismologist, from the hazard modeler, in order to understand those parameters very well. Today, what do we have? We don't have much information, so we're going to rely on the arbitrary fault rupture. We have the magnitude, the rake, the deep, the strike, and we have the hypocenter. And we're going to ask OpenQuake to generate the faulture with the arbitrary fault rupture parameter. Okay, so make sure that the ball is located here in arbitrary fault rupture, and then we were just missing the strike and the deep. Okay, so for the strike, we can see that for the strike of the model of the event that we will be modeling today, is a 348 degrees strike. The strike again is the orientation of the fault. So we're going to be modeling a fault that has 380 degrees of rotation, okay, with respect to the north. And then the deep, I think by default, it was already 90, but the deep that we will be modeling today is also for a 90 degrees. Is there any question up to here? Someone who hasn't been able to locate the earthquake rupture tab? Everything's okay. If I'm going too fast, remember that you can raise your hand. So with all these parameters in place, I can ask OpenQuake with this button right here, calculate the geometry. So again, based on that magnitude, that location, OpenQuake will come up with, based with the depth as well, OpenQuake will come up with an arbitrary fault rupture that is bounded by those parameters, that represents those parameters. And the geometry of that rupture is this one. It has a top point, top left point, top right point, bottom left point, and bottom right point. So you can have, OpenQuake is telling you the points of that rupture, and that's it. We're ready. We already have the geometry and the parameters of the rupture. Kata wants to make a comment here.
Yes, Ale, Natalia is asking, can you explain the angles with the image? I guess with the image you shared before. And Chiara is saying, what would you recommend to use as values if no info are available for strike and deep angles?
That's a very good question. Okay, so let me go to the first one, which is, could you explain the angles again with the image? So let me see if I can explain to you the angles again. So I am going to go back here. Okay. So I think you meant this image, maybe, or maybe you meant the image of the map, but here I think we can see them much better. So the angles of the block, of the movement of the block, are like this. You have the strike angle. The strike angle is actually the, let me put it even bigger. Okay. The strike is the orientation of the rupture, okay? Is the orientation of the fault where the rupture is being generated. And is the orientation with regards to the north, okay? To the true north of the earth, right? So the strike is giving us the orientation of the rupture. And the strike will be visible when we see the ground motion field, because we are seeing the ground motion field in a map, and we can see in the map the orientation of the fault. What we cannot see there, it will be the dip, but the dip is basically, the dip is the angle between the fault, you can see it here, the angle between the fault and the horizontal plane of the earth. The dip is this one right here. So is this angle that is formed between the horizontal and the plane of the fault. Basically the dip of the block that is moving either away or coming in or slipping, okay? And then the rake, which in this case we inputted 0, is if that block has a rotation component when it's sleeping. If it's not, if it doesn't have a rotation component, it's just moving as it is. And then I hope this explains to you again the angles. By the way, the presentation is shared in the OpenQuake training website as well. So if you ever want to come back to this slide and try to understand better the angles, more or less, you can always go back to the presentation and this image will be there. So basically these three angles are telling you, defining you the whole movement of the block of the earth crust that is structuring, okay? The other question was regarding what do I do when I don't have those parameters? Is there default parameters? You can use default parameters. Let's say, for example, usually rake is difficult to identify. Many sites for many earthquakes define, tell you that the events have 0 rake. I think in reality, maybe most events will have a rake angle. During a rupture, there's movement in these 3 angles, but they're difficult to identify. So usually they put rake as 0. But it's never good to have or use a default parameter when you're lacking the information. The best is to have a seismologist tell you what can these approximations of this angle be. Sometimes there is more than one rupture given to you. Even for observed events, for historical earthquakes, Sometimes the USGS says that the dip, the rake, and the strike were this. Then the national observatory of that country tells you that the dip, the rake, and the strike is these other parameters. And you can have different representations of the rupture of a single event because we even have uncertainty in these things. So in those cases, the best will be to take both possible ruptures into account in your analysis. So you may want to do estimations with both types of ruptures. So yes, again, default parameters, they don't exist. We don't have default parameters to use with the lack of information. We should always be using the best information available that we have from the event.
I can add a little bit, Alejandro.
Yes, yes, please, Kendra.
So one thing to consider is the motivation for doing the scenario analysis in the first place. So sometimes this will be because we have a specific site we're interested in, or other times it will be because we know that there is some particular hazard that we're interested in looking at. And so the ways that the latter case are usually identified are either by having some knowledge already of a fault that exists, of an earthquake that's happened in the past, something coming from the hazard model that covers that region. And in all of these cases, there are likely to be some sort of parameters that are available there. So for example, if we know that we're in a region that has normal faults, because when we look at the surface of the earth, we see the expression of a normal fault, or maybe we have recorded earthquakes that have normal faulting focal mechanisms, and we'll talk more about this during the PSHA session. That can help us to actually look at what we see on the earth, what strike angle they're expecting, and then we can use assumptions coming from, for example, Andersonian mechanics about the likely dip and the likely rake of a normal fault based on how stress and failure work. So in this example I'm giving you, for example, a dip angle might be closer to 60 degrees and with a rake of negative 90 degrees. Whenever a hazard model, PSHA model, probabilistic one, is constructed, we're intending to include all the possible scenarios inside of that hazard model. And so that means that the scenarios have already had some values assigned to them as well. So if you're deriving a rupture from an existing hazard input model, whoever developed this model will have assigned some parameters. So maybe just to summarize this, there should always be a way to come up with some parameters that are more appropriate than just assuming a default.
Whether the event is historical or is an event that you could expect to come.
Great, yeah.
Yeah. Okay, thank you, Kendra. I hope we were able to answer the question. Okay, we were able to define the entire thing, and when we click on calculate geometry, the IPT is telling us, okay, this is the geometry given by four points. So these 4 points are defining the entire fault rupture that we need, and we will be modeling today. So what is missing? What do we need now? What we need now is just to convert. Click on the button, convert to NRML, and NRML is the language that OpenQuake uses to read input files. So you just convert this information into NRML, and you can see that in NRML, this information has this format. It has certain brackets where the magnitude is, certain brackets where the hypocenter is, certain brackets for the definition of the rupture. And this is perfect. This is what OpenQuake needs to be able to do an estimate of the ground shaking. So first thing we needed, rupture done. What we need to do now is just using the IPT download button, you click on download, and this rupture plane will be downloaded as an XML file in your downloads folder. So this is my downloads folder. I will immediately do this bigger because I think just to make sure that we will be able to see. This is my downloads folder in my computer. If in your computer, your default downloads folder is something else, then look in there. The browser will download this folder, this file, whatever that folder, default folder is for you. So you can see that this rupture file, again, I downloaded using this button. click on download, and then it appears in my downloads folder. It's called Earthquake Rupture Model, and it has that information there. If anyone was not able to produce this rupture file, please let us know, and then I can repeat. If you already have it, it means that we're ready. We said we needed 2 things, or 3 things basically: earthquake rupture, GMPs, and if we want to consider side effects. Rupture, done. GMPs and side effects, now we need to input them. We input them using what we call a configuration file. A configuration file is basically telling OpenQuake what we want to do. OpenQuake has a scenario calculator, scenario risk calculator, PSHA calculator, has so many calculators that OpenQuake needs you to tell the tool which of the calculators you want to use. So we need to specify that. We need to specify where we want to estimate ground motion fields, where, in which region, etc., which GMPs we want to use, which intensity measure types we want. We said that ground motion fields can be MMI, it can be PGA, spectral acceleration. So we need to define all these things for OpenQuake in order for it to produce the ground motion fields. All of this is done through what we call a configuration file. Can we create a configuration file using the IPT? Yes, we can. We just go back to the IPT. So I'm going back to the IPT right here. So I am back in the IPT, and you can see that the IPT within the tabs has one called configuration file. Okay. So in this configuration file tab, we're going to click on that tab, and we will be able to see that using this particular tab, we can create a configuration file for a OpenQuake calculation. As I was telling you, we can create a file for earthquake scenarios, for stochastic event-based, for classical probabilistic PSHA. Today, make sure that you are on the tab configuration file and you are on the tab of earthquake scenarios. Okay, so make sure we are configuration tab, earthquake scenarios, and choose which components of your configuration file and related fields. So we will start here telling OpenQuake what we want to do in this calculation. First thing, this is a hazard calculation only. There are no buildings, there are no vulnerability curves. It's just the ground motion fields. We only want to estimate ground motion fields. So we need to make sure that this check is on the hazard, okay? Then the description of the calculation. The description of the calculation will become the name of your calculation. So for the description, we always recommend to put a descriptive yet short sentence. So today, for example, I believe this is an event of magnitude 7.0 in Colombia. Okay, so that can be my definition of my description of today. I will put in parentheses because first we are going to be estimating the median prediction of the ground shaking intensity. Let's write here median to differentiate this calculation from the next one that we will use that will have the variability. So for our description of today's of this particular calculation, it's event magnitude 7.0 Colombian, and I'm putting median. You can be as descriptive as possible if you want to put here that the rupture is San Jeronimo, that the deep is 90 degrees, that the depth is 15 degrees. You can put all of that here. And that means that if in your next calculation you want to make a different depth for the earthquake, for example, then you can put that in the description and you can easily see it. You will be able to easily see in the list of calculations. This one is the one with the depth of 10 kilometers. This one is the one with the depth of 15 kilometers. So be as descriptive as you want here. There is no problem there. So I'm putting there events, this event, Colombia, and the median prediction. Perfect. Rupture information. Since this is a configuration file for an earthquake scenario, OpenQuake is expecting you to have a rupture file. A file that defines all the parameters of the rupture, the angles, the magnitude, the depth. We already did that. It was the first part that we did. So we can look for that file in our downloads folder. So it is right here. This is my file. I will upload this file to the configuration. Okay. So I click on the upload button. It brings me the Windows file explorer, or it will bring the Mac file explorer. Just go to where your file was downloaded and double click on it. and then you have it, okay? It means it's saying here that the file was uploaded successfully. If you use OpenQuake frequently, you might have more than one rupture. So here in this list, you might have this rupture and other ruptures that you use. Make sure that the one for today is highlighted in blue, is the one that we'll be using today. So if you have in this drop-down many ruptures, just click on here and make sure that the one that we created today is highlighted here. This one is called earthquake rupture model.xml, okay? I only have one in my downloads folder, so it's easy to identify. Rupture mesh spacing is the next parameter. So OpenQuake needs us to define the rupture mesh spacing. What is that? This is the first non-trivial parameter, let's say, that the IPT is requesting from us. Usually, most parameters have this question mark here, which means that if I don't know very well what the IPT is asking from me here, I can just hover the mouse over the question mark, and the question mark will give us a small, brief description of what is expecting for us to input here. What is the rupture mesh spacing? So according to this definition, it says, let me hover on top of it. A parameter used to specify the mesh size used by the OpenQuake engine to discretize the rupture. Note that the smaller the mesh spacing, the greater will be, one, the precision of the calculation, but two, greater will be the computational demand, okay? What does all of this mean? It means that we're making a model, right? So a rupture is, I think let me see if I can. Okay, so this is my rupture. Let's say this is my fault, my trace in the surface of the rupture. If I am here, I need to calculate my distance to the rupture, okay? So this parameter, what it will do is simply discretize the rupture into different points, and then I can calculate my distance to the rupture, however I discretize it. And then the finer this discretization parameter, it means that the finer will be that mesh of points, and the more accurate parameters like my distance to the fault will be, okay? So the higher the discretization, the better my parameter is, or the more realistic my parameter is. The setback is that the higher the discretization of the rupture, the more computational time it is needed to make the calculation. That is fine. Usually people ask us, okay, so what is a default mesh spacing parameter? We can leave it at 5. 5 is a good rupture mesh spacing. If you're afraid that this parameter might be too gross, you want to do a finer discretization, you can always do this. Put a different parameter here, let's say 2, and then check what is the difference or the variation in your results by making this parameter different. If there is no difference, it means that the rupture mesh spacing of 5 kilometers was appropriate, and then you can be confident that the first calculation was good. This is how we identify optimal parameters. People usually, it's always asking us, well, what should I use here? What is the optimal parameter? The optimal parameter is the one that allows you to run the calculation without having a huge computational demand, but without affecting your results. It means that you have found the best parameter for you when you achieve those two things. Okay, so let's leave rupture mesh spacing as 5 for now. I encourage you to explore if there's any difference in the results that we will be estimating today if you use 10 or 1, let's say. It's a nice exercise for you to do. You will see that the calculations are quite fast, so it's very easy to generate multiple calculations when we're doing scenarios. Hazard sites, okay? So what does hazard sites mean? I already told you this is the earthquake that I want to be modeling today. This is the rupture mesh spacing that I want to use. But where do you want the ground motion field? So these intensities that we're going to calculate in the surface, where are they? Okay, so what we're going to do is define a grid of points where we want the intensities to be calculated. This grid of points should include the region that I'm interested in. For example, the city of Medellin. Okay, so if I go back to the image to this image right here, this image contains the region where I want to estimate the ground shaking intensity. Medellin is inside this particular rectangle, this grid. Medellin is actually right on, very close to the fault origin, to the rupture origin. But we also want to see what is the intensities in other towns within this region. So basically, in this parameter, region grid or hazard sites, we're going to give the IPT these 4 points, this extent of the region, and it will calculate the intensities within that region only. Why do we define a region? Because if I am interested only in the cities in here, then if I put a bigger region, OpenQuake will lose time, computational time and demand, calculating intensities in sites where I am not interested. So that's why it's important to sometimes bound the location, to manage the calculation, to make the calculation useful. So let's input these parameters. Hazard sites, today I'm providing a region grid with 4 points, okay? I will later tell you what list of sites and exposure model do. So let's input, first of all, the grid spacing. So within this grid, at what is the discretization, the amount of points, the separation of the points that I want within this region. Let's say I want points every 2 kilometers within this rectangle. In that way, between this point and this point, every 2 kilometers, I'm gonna have a point with my shaking intensity. And I'm going to provide the region coordinates. So the region coordinates, according to here, first we're going to provide the first point. The IPT doesn't really care the order in which you define the first point. So it really doesn't care which is the first point that you define. Okay, so you can define first this point, or this one, or this one, no problem. It is, though, required for you to keep a convention. If you define this point, your next point should be counterclockwise, or it should be clockwise, okay? But it cannot be crossed. You cannot define this point first, then this point first, then this point then, and then this point. You cannot do it like this. It always has to follow a convention, okay? So let's start with the top left point, okay? So let's start with that one, negative 76.7 is the first longitude, and then 7.2 is the latitude of that first point, which means that my next point, I will try to use this one. I am going following this convention, so I'm going to, my second point is going to be negative 74.4, latitude 7.2, okay? Then my third point is this one, is below, following this convention. This is my next point, 74.4 longitude and latitude 5.3. Okay, perfect. We ran out of spaces, okay? And so far we have only defined a triangle, right? We have only defined these 3. I need an extra point, so I just click on new row, and then a new row appears for me to define the final point, which is negative 76.7, and the latitude is 5.3. Okay? Perfect. I have already defined that I want, I have my rupture occurring here, and I want to estimate ground shaking intensity within these regions, and I want points every 2 kilometers. Anyone here who hasn't been able to follow me, am I going too fast? Feel free to raise your hand and tell me. Very good, because today we just want to visualize the ground shaking and the ground motion fields within this region. We're done. I also have the option to provide the IPT with a list of sites. So let's say I'm only interested in a couple of points, 1, 3, or 4 points within this region. Maybe there are power plants located there. Maybe there are hospitals located there. And I don't want OpenQuake to lose time estimating ground shaking in places where I don't have things of interest. So I can just provide a list of sites and then longitude, latitude, and this site. This is provided in the shape of a file, and then OpenQuake will calculate the estimates. The ground motion fields will only contain these points. Another thing that I can do is I may have a lot of sites, an entire exposure model at my disposal, which means a risk modeler already created an exposure model for this region. In other words, how many houses there are, where are they located, what are their characteristics, And with these locations of all of those houses, all of those points of interest, with this exposure model, OpenQuake will calculate the ground motion fields only for those locations. And then it means that for a risk computation, it's more efficient because the ground shaking will only be estimated where we have assets. Okay, so that's the difference between these options. Today, we don't have assets, only have this region grid, so we're going to be calculating this grid. Okay, perfect. Going back to full screen here. Site conditions. Okay, so are we estimating our intensities in a steep soil? Are we estimating our intensities in a soft soil? Are we estimating intensities with different conditions of soil depending on the different assets that I have? We have all those options to model with the IPT and in OpenQuake. Today, we're just going to assume that the entire region is a steep soil, okay? And eventually we will see how this has an impact in risk. Next week, when we do our calculations, we are going to be using site conditions. In other words, we're going to be considering the soils of the city that we will be modeling, okay? Today, we're not interested in that. We just want to see how those ground motion fields look like and the different assumptions between GMPs. So today we're going to be using the default uniform site parameters, which are a BS30 of 760. This is inferred, and you should leave this in 100 and this in 2. Okay, so we're not going to change anything here, which means that we will be doing our estimations of ground shaking on a very steep soil. So we already decided where we want the hazard to be calculated. We already know that we want the estimations to be on steep soil. We're only missing the GMPs and how many ground motion fields we want to produce, okay? First, the GMPs. Which GMPs are we going to use? According to this slide, to this educational exercise that we're doing today, not a real exercise, we're going to be choosing 3. ACAR Canyon 2010, ACAR with hypocentral distance 2014, and IRIS 2014. Kata, I see you raise your hand. Would you like to make a comment here?
Hi, Ale. We have a question from Fernando. If you could please briefly mention what BS30 means.
It's a very good question. This is a very good question. I am going maybe a little bit fast, and but if you feel that any of these terms that I am mentioning are not familiar to you, please feel free to let us know, because the whole point of the workshop is to be an introductory course for you. Okay, so there is no silly questions, there is no simple questions. Every question is very good. And since many of you are not familiar with these topics, it's very important to ask that. So what is BS30? I mentioned a BS30 term here. When an earthquake occurs, it is happening, usually the rupture is happening below ground, right? So it's not happening at the surface, it's happening below ground, which means that the earthquake waves need to travel through the ground and reach the surface. While they displace through this medium, they can get amplified by the material of that soil substructure, let's say, they can get amplified by the quality of the soil. And sometimes it's common to hear engineers, a soft soil will amplify your shaking. And this is true. Soft soils tend to behave like a gelatin, right? So they start amplifying the motion much more. Maybe the earthquake wasn't that strong. Maybe the earthquake was too far, but because the waves are traveling to this medium, which is soft, on the surface, you're going to feel an amplification of the ground shaking intensity, okay? So first comment is very important when you're modeling risk and hazard to take into account the site effects, okay? Otherwise, you might be misrepresenting the danger, right? How do we account for that? How do we account for that amplification of the ground shaking intensity? One of the ways we do this as engineers is we take a measurement of how stiff the soil is. What we do is we create holes in the ground, we put microphones in the ground, and then we detonate we make some noise. Usually we detonate like a small seismic charge or something like that, that will generate waves. And then those waves are captured by the microphones. The speed of those waves, how fast they travel, is a measurement of how stiff the soil is. And with that stiffness, we can understand if the ground shaking intensity will be amplified or not. That velocity, the speed at which those waves travel in a particular strata of soil, is what we call the BS30. It's basically the velocity of a wave, of the shear wave, at 30 meters of depth, okay? So we put these microphones right there, we measure that velocity, and we use that velocity to understand if the ground is stiff or if it's soft, and with that, we amplify the ground shaking. That term, BS30, is a very engineering term. Every time you hear the term BS30, think about how stiff the soil is, how fast was the wave traveling. So BS30 is the main parameter that we use to understand from geotechnical engineers how steep the soil is. I hope I was able to answer that question in this simple manner. If you have any other question regarding anything else, please let us know. Today we're not using any BS30 data. We don't have this data collected for this particular region. We're just going to assume, because today is just a study case, that everything is on rock. Next week, we're going to be using a file that contains that information for a city, okay? So we might be able to explore that file, and we will look how that looks, but basically it's a file that for every asset that we have exposed in our study region, we have the BS30 value, we have how stiff the soil is there, and then the GMP will know how to amplify the shaking intensity. That median ground motion shaking plus the variability will get amplified by that BS30 value. Okay, so that is the explanation of what BS30 is. We're going to be using 3 GMPs here. Akar Kanyan 2010. So the first one is Akar Kanyan 2010. To specify the GMPs, we click on in here, and then we see the whole list of GMPs there, but we can simply by writing the first letters of the GMP we want to use, the menu collapses and it's easy to find. Akar Kanyan 2010 is right here. We just click on it, and then we can see that it gets added in the menu below. That means that the GMP has been selected, okay? The second GMP, again, I click on there. It's also AKK, Akar Kanyan with hypocentral R 2014, okay? And then the third and last one will be Idris. So IDR already collapses the options into this one. So Idris 2014 or Idris 2014. And I click on it and I can see they have been added to the set of GMPs that I want to make calculations. So OpenQuake already knows, okay, you want me to make estimations of ground motion fields using these 3 GMPs, okay? The nice thing is that these GMPs use different parameters to measure the distance with regards to the source. So the point is that we will be able to observe, to a study, what is the difference in the ground shaking that it gets estimated according to each GMP. So we will see the effect of the assumption of GMP, of each GMP in the ground shaking intensity. Very good. Now specifying the IMT. The IMT is the intensity measure type. Do you want PGA? Do you want spectral acceleration? What do you want those ground motion fields to be in? I will click here on PGA. If you are a civil engineer and you're interested in, for example, how is the ground, the spectral acceleration from a given event, you can choose the spectral acceleration that you want. Let's say PGA is the one that we will explore today, is that maximum shaking that gets reported in each particular point. We're interested in generic ground motion fields for that particular shaking metric, okay? And that's it. We are now ready to tell OpenQuake the following things. Do we want a median prediction, or do we want a median plus the variability of the GMP in the ground motion fields? First, we're going to simulate only the median. How do we do this? We specify as the level of truncation of the equation as 0. What does that mean? What that means, I'm going back. What that means is that I want my estimations of ground shaking to be the median plus a 0 deviation from the median. So basically what the equation will come here is going to look, the GMP is going to look at its median. Okay, this is my median prediction for this site. And this is the distribution of the variability of that I can apply. But I am saying apply a 0 deviation from the median. So instead of going the median plus an aleatory deviation from the median, is going to take only the median. So truncation level 0 means let's take 0 deviations from the median. So what we are going to get here is a ground motion field that looks with that smoothed attenuation. Okay, so we're going to do that as part of the exercise, first with 0 variability. Later we will ask for it. Okay, so level of truncation here 0, median plus 0 deviations from the median will give me the median estimation. Maximum source to site distance, we're going to put here 200 kilometers. What this means is beyond 200 kilometers from the source, don't estimate ground shaking intensities. I'm not interested in anything happening beyond 200 kilometers, let's say. And how many ground motion fields do you want? Okay. Basically, if I am asking for only the median ground motion field, I should ask only one ground motion field for each one of the GMPs that I have. Why only one? Because asking for more than one is pointless because there is no variability in this equation. I am asking the calculator to give me always the median plus 0 random deviations from the median. That 0 random deviation from the median will always give me the median, which means that asking for more ground motion fields will be trivial. Okay. We can ask for many more ground motion fields when we want variability to be included, okay? Because it's an aleatory variability. We want to generate many. So all the uncertainty, all the variability of the shaking gets sampled, okay? So for this first calculation, we are done. Let's check the parameters together. Description, event magnitude 7.0 in Colombia. We make sure that our rupture file is selected in blue. Rupture mesh spacing, let's make sure it's 5. Hazard sites is a region grid, a set of points every 2 kilometers within this rectangle. Site conditions, stiff soil, 3 ground motion models, and 1 ground motion field per model with 0 variability. So the result of this calculation is going to be 3 ground motion fields. One for a Carcagnan 2010, one for Etal hypocentral depth 2014, and one for Ibris, okay? We are done. We are ready to run this calculation. The only thing we need to do is we need to download this as a zip file. You click on that button, it will download the calculation as a zip file. And then I always rename this because I like to, you know, in my downloads, I understand that this is the median calculation, let's say. So I know that this SIFT calculation is my median. Perfect. We are ready to run this calculation. But since we are already here in the IPT, let's prepare the calculation considering variability as well. What changes when we consider variability? Only 2 parameters. The first one is the number of ground motion fields that I want. Let's ask OpenQuake to give me 10 ground motion fields per each one of the GMPs or ground motion models that I have. Okay, so now OpenQuake will generate 10 ground motion fields for each one. But I also need to change the level of truncation. Okay, so I'm going to put here back a 3. It can be a 1, it can be a 2, it can be a 3, it can be a 6. What we are telling OpenQuake with this is you're going to generate 10 ground motion fields for this particular GMP. Those ground motion fields, each one of the points in that ground motion field is going to be your median prediction plus a 3 sigma variation of that median, okay? And that will be sampled randomly. Sometimes OpenQuake in this particular first ground motion field, it will, in this particular point, is going to sample something stronger than the median. And in another point, is going to sample something lower than the median. Sometimes that deviation will be very big because I gave it the limit of up to 3 deviations from the median. It can be 2, it can be 1, it can be a little bit less than 1. It will never be more than 3 because I specified specifically 3. If I put 6, then it will go even farther to sample aleatory, knowing that the farther I am away from the median, the less likely it is that it will be sampled because it is a less likely observation, okay? But this is why we need to ask, when we ask for variability, we need to ask for more than 1 ground motion field. We need to ask for many. So the entire uncertainty of the GMP is modeled. Always the question, how many ground motion fields should we should we ask for if I want the full variability of the GMP done? Usually, and these calculations are very fast, there is no problem if you ask for 1,000 ground motion fields, for 2,000 ground motion fields. When you ask for this amount of ground motion fields, all of them get generated, and then you are sure that you are sampling all the variability of your GMP model, okay? When you're modeling risk, this is very important. You do not want to model risk with a median prediction because it means that you will be underestimating your risk. So for risk, you don't want to consider that the earthquake can happen only in one possible way. You want to model many ways. You want to model that observed variability that nature has when the ground shaking comes. So for one particular event, and this is what we're going to do next week, we have a real city, we have real buildings. In that case, we're going to ask for 1,000 ground motion fields, okay? And then we're going to see that it is important to consider that variability. So for now, let's go into ask. This is just a study example. You can ask for 1,000. It will just take the calculation more time to execute. But today, let's just ask for 10 for this particular calculation with variability. And I only need to change the description of this one to variability. And then that way, this one is different from the previous one because this one includes a level of truncation 3 and 30 ground motion fields, 10 for each one. So just click on the download zip file, and this calculation is also ready to be run. I am going to rename it to seismic hazard bar calculation, let's say. Okay, perfect. Raise your hand if you were not able to follow me up to this point. Everyone has, okay, perfect. So now we're going to run the calculation. Is how do we run the calculation? We go back to the OpenQuake engine, okay? We go back to the OpenQuake engine, and we're going to say run a calculation. And basically we click here, and we go and look for our median calculation first. We double click on that zip file, and that calculation will be run for us. So you can see the description of my calculation appears there. I am running now the event of magnitude 7.0. Again, how do I run the calculation? Click on run a calculation, look for the zip folder that contains all the input parameters, and then double click on it, and the calculation will be running. You can see that my calculation for the median ground motion fields is already finished. Let's run the calculation for the ground motion fields with the variability, okay? And then you will see that the calculation will be running. Most important question of the workshop: do your calculations, do they appear in green? Green means that the calculation was run successfully. Does anyone have a calculation that appears in red? It failed. The calculation failed. Please let us know. A calculation can fail because I forgot to put the minus in the hypocenter, so the earthquake is happening far away. There are many ways in which the calculation may have failed. How do we look into a possible explanation of why the calculation failed? You can click on the outputs here, on the console button, console. And the console tells you basically the record of the calculation. So it tells you, okay, you're using OpenQuake 3.16, you're doing an event, and then I finished successfully in this case. in your console, if your calculation is red, you are going to see an error. If you have an error, please write on the chat or let Kata know what is the error, and that way we can provide some assistance. So I see only one hand raised in red. Saula, did you have an issue running the calculation?
I've got my problem. I just can you hear me?
A little bit. Can you repeat?
I fixed the problem.
You fixed the problem. Okay, perfect.
Yeah.
Okay, great. So not red calculation. So I think we all deserve a big applause, because it means we all we have,
yes.
or no, we have.
Yes, no, Fio Ma'am is telling us if you could show again how to run a calculation, please.
Yeah, sure. It's you click on this button, run a calculation, you go back to the web UI, right? We were here in the input preparation toolkit. The button won't appear here. You need to make sure that you're back again on the tab of the OpenQuake engine, and then you click on run a calculation, and then you look for the zip folders, okay? If by any chance you missed or you closed the engine and you're still here, you can just reopen it by clicking here on the tab that says engine. So click on engine, it will bring you back to this screen. In this screen, you click on run a calculation, and you look for the zip folder in the folder where your browser downloads the files. So very good. This is if your calculation is green, it means that your ground shaking estimates are done. They are in your computer. You can explore them. You can see them using Excel. You can see them using ArcGIS. You can see them using QGIS. Any way you want to visualize the results, you can, okay? So this marks the end of the exercise using OpenQuake, let's say. So we've used OpenQuake. Green calculations means we finished and it's successful. We have 20 minutes, more or less, left on the workshop. So in these 20 minutes, I am only and simply going to show you how to visualize those results with QGIS, okay? Some of you might be, go ahead, Kata.
Yeah, sorry to interrupt before you move. So there are some people that say executing in the web UI. The status says executing, and it's asking, is there a way to figure out why it is taking so long?
Yes. If it's taking very long, make sure that you, for example, I don't know which of the calculations you're running, but if you ask for 1,000 ground motion fields, it will take longer than usual. In this case, I asked for 0 for 1 ground motion field in the case of medium ground motion fields, and for 10 in the case of variable ground motion fields. Usually that takes seconds, 3 or 4 seconds. If your computer is taking a lot of time, it's because probably it's using a lot of memory from somewhere else, not from OpenQuake. So if you have Spotify open, you can close it. If you have YouTube open, you can close it. If you have Word, Excel, many things open, make sure you close them because that is draining a lot of the computer's RAM. And then the engine needs RAM to be able to run these calculations fast. But as long as they're running, you will be able that they eventually turn green and they finish. Tell me, Kata.
Yes, and also Priyanka was asking if you could repeat again how you decided the number of ground motion fields in the IPT.
Yeah, sure. So here on the IPT, for the variability, I decided to go for 10. 10 is by no means enough ground motion fields. You should have, as I was suggesting, you can put 1,000, 2,000, and that's fine. Why did I choose 10? Because I don't want calculation for this exercise to take a lot of time. I want to be ready to show you the results. So I put 10, which will be just sample 10 from each one, and that will be very fast, I know. And then this won't consume much time for us in the workshops. What I encourage you to do is next week, when we are doing real risk calculations, we have buildings, we have people, we will be estimating damage, dollars lost from this event. In the next session, I highly encourage you to see what happens if I choose 100 ground motion fields, 1,000 ground motion fields, and see the difference in risk. I will spoil it for you. The conclusion is, when you're modeling a rupture, you always want to make sure that you're considering enough ground motion fields in order to not underestimate the risk. I do that by using thousands of ground motion fields. You can start with 1,000 and see the results, then 2,000 and see the results. If there is no variation, it means that with 1,000 ground motion fields, I was able to sample the whole variability of the GMPE, and then my results include that variability, and those risk results are not underestimating the risk, let's say. So that's how we choose the number of ground motion fields. In this case, I put 10 because today we're not seeing risk metrics. I only want to focus on the difference between GMPs, and that's it. So as I was saying, very good. We are done. We finished the following part. If you want to follow me, because what I want to show you now. So all of you have the results, and I highly encourage you to explore it. Explore each one of them. They are explored by clicking on the outputs button. So here on the output button, you have a file, an output file for the number of events, the full report for the calculation. You have a file for the ground motion fields. So you can download the ground motion fields as plain CSV files and files that Excel can read. But so the calculations are done, and you can choose any way for you to visualize the result. Here, if you want, you can follow me, and I will show you how we can visualize the results using the OpenQuake QGIS plugin. It's a plugin that we have developed for the QGIS platform. And then it has certain features that would facilitate for us to visualize the results. It's very good for intermediate users of OpenQuake because it means that you can easily visualize the results. Expert users will want to visualize results in QGIS, in their source code, in any other type of code that they want. So from now on, just follow me and I will show you this additional tool that OpenQuake has. So how can we visualize these results? Let's do something. Let me close all of this. Let me close the presentation. Let me go to my desktop. And in the folder of today's exercise, it's already unzipped for me. I'm going to go inside the folder, and in the material of today's exercise, there is a small .qgz file, is the GIS project file of the calculation. Double click on there, and it will bring you some information that Kata and I have prepared to visualize today's exercise. So what we are doing here, for those of you that are not familiar with QGIS, if you don't know how to use it, I highly encourage you to see some YouTube videos on what is QGIS, how do we use it. Basically, QGIS is a software for visualizing geographic information systems. So a ground motion field, which is a set of points with longitude, latitude, and an intensity measure, it's a geographical information. So I can visualize it with QGIS, with ArcGIS. I can visualize it with any software that allows me to see geographical information. So this is how QGIS looks like. For those of you who are not familiar with it, for those of you who are not familiar with this, you can simply see me on screen, follow me on screen. For those of you who are very familiar with this, I will just show you very fast how we can install the plugin and visualize the results. So this is the QGIS. I'm seeing the map of Colombia and my region. All of this is information that Kata and I have bundled and prepared for you. The first thing we need to do here is to install the plugin that will communicate QGIS with OpenQuake. So I already said OpenQuake results are already there. So we just need the plugin to communicate QGIS with the plugin, with OpenQuake. This is done through, follow me here, plugins. Very important. There is a button here, depending on the language of your QGIS. If it's in English, it's called plugins. If not, it's in other words, similar for your language. You are going to click on Manage and Install Plugins in the first option that comes available. This is going to bring this window, okay? And in this window, here on search, you can make sure that you want to search all the plugins that are available, and you want to, if you write here OpenQuake, just by writing OpenQuake, it already appeared. This is the plugin that you need to install. It's called OpenQuake Integrated Risk Modeling Toolkit. You click on that, highlight it in blue, and then you make sure that you click on the icon that says Install Plugin. Okay, so you make sure you install it, and then that is going to bring install the OpenQuake plugin that is compatible with your software. I will repeat once again, how do I install the plugin? You click on Plugins, Manage and Install Plugins. In all plugins, I write OpenQuake, and you can install the plugin, okay? And you can see that my plugin, I already have it installed. My plugin is the version 3.16 of OpenQuake, okay? Which is compatible with the version of OpenQuake that I have installed. Okay, now, I will go fast because we have 10 minutes left on the workshop, and we have some questions that we want to ask you after the workshop and things like this. So I will just follow me here on screen. Don't follow me on your computers. Just follow me here on screen, and then you can try it on yourselves later on. I just want to show you how you visualize the results. Once you install the plugin, these buttons will appear here on the menu. There are blue and white icons right here. This particular play button will bring the OpenQuake plugin of QGIS. This plugin is basically a user interface that is analogous to our OpenQuake web user interface. You can see that I have these two calculations there, and we have these two calculations right here. Okay, so I have the median and the variability. Through the plugin, I can click on one calculation, highlight the calculation. I want to say explore the results from the median ground motion field estimates. And then let's say I want to bring a layer. I want to bring the information from my ground motion fields. So with the calculation highlighted, I can load the layer using this button. And I can choose which ground motion field I want to bring. 0 for a car canyon, 1 for a car with hypocentral R, and 2 for hybrids. Okay, so let's bring a car canyon first. I will click on OK, and I want to bring the PGA ground motion field. Okay, so I click on OK, and voila. The plugin has brought here the ground motion field for a car canyon 2010. So for the region where I asked for the ground shaking estimates, this is the median prediction of the ground shaking for this magnitude 7 event with this origin here. And you can see that the range of ground shaking intensities here, according to this particular GMPE, this event can have a ground shaking intensity close to the fault. Look at here, close to the fault, we have almost 0.34 Gs of ground shaking intensity close to the fault. Out of the fault, we can have much less intensity. So we can see that the intensity attenuates with distance in this case. Remember, this is the median prediction of the ground shaking intensity. It looks very smooth. It's following that median ground shaking intensity. I am going to bring the other ground motion field from not a car canyon 2010, but from a car with hypocentral distance. Okay, I encourage you to do this by yourselves. When the workshop is over, you can do this by yourselves. I want you to take a look at this. This is the initial ground shaking prediction, right? With a car canyon 2010. And look, it goes from 0 to 0.34 Gs. Okay. This is the ground shaking prediction using a car canyon with hypocentral depth. Now notice the differences. This one is also giving us estimates from 0 to 0.38% of acceleration. So let's say in terms of how much acceleration they are predicting close to the source, it's similar, right? 0.34, 0.38, let's say close to the source, they're giving me similar predictions. The thing is that because this one is considering my distance to the source as the distance between the point and the hypocenter, you can see that the spatial distribution of the ground shaking is very different. It's simply all distances are pointing towards that single point, hypocentral distance, whereas for the other ground shaking has this high ground shaking along the fault trace following that strike of 348 degrees, because for this GMPE, it is using my distance to the source as my closest distance, not to the hypocenter, but to the projection of the fault in the surface. And so what I want you to know is that there's huge differences between GMPEs. What we want to say is that each GMPE, because of the parameters it uses, will give you very different predictions of ground shaking, okay? And then last but not least, what I want to show you is I'm going to bring the same Akar-Kanyan 2014 prediction, but with variability. And we're going to observe something really interesting. I will finish by showing you this. Look at the difference between this ground motion field. This is one of the many ground motion fields that I asked. I asked 10, if I'm not mistaken. I asked for 10 ground motion fields, including 3 sigmas of variability. Look at the shape of the shaking intensity is different, but also look at the range of the intensities. Without variability, this GMPE was telling us that the highest ground shaking I can experience close to the source was about 34% of the acceleration of gravity. With variability of 3 sigmas, the highest shaking that I am sampling, the highest shaking that this GMPE is telling me, is that I can experience almost or above 2 Gs of ground shaking for this particular event. What does this mean? By considering not the median, but the median plus a big deviation from the median in my modelation of ground shaking intensity, it is possible to observe some points that have higher ground shaking intensity than the one predicted by the median, and some others very low from the median. We can still see that sites close to the source will have higher ground shaking intensity, but the variation is quite strong. So again, it's completely different. Imagine if we were modeling risk. It is completely different modeling risk using this intensity or this intensity or this intensity. So stay tuned for next week, because next week we're going to see what is the influence of each one of these assumptions in risk estimates, okay? So I finish here. Thank you very much. If you have any questions, I'm happy to answer them. We only have some minutes, so please stay here. We have some questions for you. So I give the word back to Kata so we can ask those questions. So thank you very much. I hope I was able to explain to you the main concepts, and I hope to also provide assistance for you in the future while you're working on yourselves, doing this exercise by yourselves. Don't forget, you can write us an email. You can send us some message if you require some help. So thank you very much. I hope this was useful, and I'm giving the word back to you, Kata.